I've been saying in words that you can think about the temperature and the speed being related, and that a higher temperature gives you a higher speed, or a higher speed gives you a higher temperature, either way, and then that relates to the pressure, so that the larger the speed of the particle, the higher the pressure that the particle is going to be exerting on the walls of the container. And so I want to just go through that so that that's actually clear to see how we're doing this, okay, to see why this makes sense. And it's not just to torture you with algebra, it's to make you think about what's happening here with regard to a microscopic view of an ideal gas, where we have to think about some specific assumptions we're making with regard to this microscopic view of an ideal gas. We have to think about the fact that the separation between the particles is large compared to their actual physical size. This means that they won't have any quantum mechanical type interactions, that we're just dealing with an actual microscopic but not quite quantum mechanical view, so we can treat these identical particles as individual things that can then interact with the walls and with each other. And they're going to do that elastically. So they're not actually going to be losing any energy through this process. Okay? They're not going to be losing any momentum through this process. Okay? And I feel like I should make a caveat to saying that the energy situation could change slightly, but the conservation of momentum will still be true, and we're talking about an elastic collision with regard to what is going on with both the walls and with each other. The other part of this is that we have to remember that Newton's laws of motion will apply to each individual particle. Okay? So that it'll work on a whole, but everything will be moving randomly. Okay? Each individual particle will have its own different journey around this container, whatever container it's in. Okay? But they will all, on the average, act the same way. So let's imagine that we have a box, specifically a cube, of side D. Okay? And we're going to have a particle that is in this box that is moving to the right. And so the speed of our particle equals positive Vx. Okay? So the momentum of our particle to start with is equal to positive m Vx. If this makes an elastic collision with the wall, and the wall is much, much, much more massive than the particle, then what is true about the velocity of the particle afterwards, the velocity of the particle after a collision is minus Vx. So it's going to be the same speed, but in the opposite direction. Okay? So the change in momentum of this particle in the x direction is equal to P final minus P initial for that particle in the x direction. So that's going to be minus 2 mvx minus positive, it's going to be minus mvx minus positive mvx, which gives you minus 2 mvx. So, and let me make sure to be consistent with the notes that I gave in class. I'm putting a little subscript P on that M there to make sure we're talking about the particle's mass, not any other mass. So the change in momentum of the particle is equal to minus 2 mp Vx. If we have conservation of momentum of the system, then what is true about the momentum change of the wall? The momentum change of the wall is going to be positive 2 mvx. So due to conservation of momentum, the change in P of the wall is equal to positive mpvx. Okay. So why am I bringing this up? Because we want to see how that relates to force. And how that relates to force, we have to remember that F, the force acting on the wall because of a particle, is equal to the change in momentum of the wall in some time period. F equals delta P over delta T, and we're talking about the wall here in question. So the force acting on the wall by a particle is equal to the wall's change in momentum divided by the change in time for some period of time as this force is being applied. Okay? And this is just in the x direction from one particle. Okay? So that means that we can put that up in here so that we get the force acting on the wall because of the particles hitting it in the x direction is equal to positive 2 mp Vx divided by delta t. So we don't want to leave the delta t here if we don't have to, so let's think about a specific time period. We have this particle moving to the right, and then we'll bounce back, move to the left, and then it will also hit this side of the container and bounce back the other way. So let's make our delta t be the time it takes to hit the right side, go to the left, and hit the right side again. So let delta t be the time to hit the right side of the container twice of our box. Okay, so the distance covered by this particle in that time period is, it goes d this way, and then goes d back that way. So that means that the distance is covered is 2d. So the velocity then, which is defined as the change in distance over time, would be the distance that's gone, which is 2d, in a given time period, delta t. So that means we can rewrite delta t as 2d over Vx. Okay. So now I'm just going to plug that back into here. So F wall, acting in the x direction, is equal to 2 times mp times Vx divided by 2d over Vx. So the 2's are going to cancel. The Vx is going to come up here in the numerator with the other one to make it squared, and we're be left with the mp over d. So F wall in the x direction is equal to mp Vx squared divided by d. Okay. The overarching goal here, as I mentioned before, I think I mentioned at the beginning of this, is that we want to look at how to relate the speed of the particles, and specifically the kinetic energy of the particles, with the pressure that the particles are exerting on the walls of the container. So we're getting there. We have force, and we have something that involves velocity, and specifically is starting to look like kinetic energy, where kinetic energy, remember, is 1/2 mv squared. So you want to make this side look like that, and you want to make this side look like the force per unit area. So we're almost there, but this is only the velocity in the x direction. And we could have many particles that all have different values for this velocity in the x direction. And so what we have to do is we have to take that into account and realize that we need to recast this v as something else in terms of the whole system. Okay? So again, this is just for one particle. The force on the wall from one particle is equal to mp Vx squared divided by d, and that's only in the x direction. But we do have the y direction and the z direction that particles could be moving in. Remember, we have a whole system of particles that are moving randomly. So they'll have some component in the x direction, some component in the y direction, and some component in the z direction. Okay? They could be non-zero, they could be zero. And so you have to think about all of those. So the important thing here now is to think about this in terms of all particles.